we are presenting Scott Nickle, HU, How Do We Know? Scott Nickle is the son of a radio and TV engineer who kind of fell into Silicon Valley by accident. He has worked in the tech industry for about 28 years with about a decade hiatus as a videotape rental entrepreneur. After his last tech employer company was bought out by a competitor in order to kill it, he found himself unemployed. Fortunately, he was in a financial position where he could remain in the valley on minimum wage, so he went to work at Barnes & Nobles, where he discovered that peddling knowledge is his true calling. He is an atheist due to his love for science, but he considers that label to be among his lesser qualities. Everyone, let's go ahead and give a nice round of applause to Scott Nickle. Who I also want to note is a great guy. He's a great friend of the group. So, Scott, we're going to get you the headset real quick. Sorry. It's already taken. Yeah. I don't know how we've somehow got here. But we're here. Put this on your hip. Okay. I'm going to put this on like reverse sunglasses.
Testing. It's working? Okay, great. Okay, let me get out my trusty notes.
Let me get you your images too.
Okay.
Scott has a number of pictures. You want to start with this one?
No, the 4 elements. That one.
Left and right.
Okay, great.
They might not be in order.
Sure, that's fine. Okay. Okay, good evening, everybody. Thanks so much for showing up. It's great to see you all. Okay, what's going on? It's moving already. As I said in my description of this talk, this was inspired by an incident that happened to me. Why does this keep spontaneously changing? Okay. Anyway, this was inspired by an incident that happened in my 5th grade science class when my science teacher told the whole class in roughly 1970 that... Oh. Yeah, this is the way Sean left it for me here. Pause. Okay, come on. Okay. So this was inspired by my 5th grade science teacher who in approximately 1970 told the whole class that H2O was just basically our best guess as to what the formula for water is. It could be H4O2, H8O4. We just picked H2O because it was the simplest one and we just went with that. She was about 110 years out of date with that piece of information. I'm not quite sure why a professional science teacher would be in that situation, although she was very conservative. Maybe she got her education from Bob Jones University. I don't know. Anyway, even today, the history of science is taught very little. Get yourself a chemistry textbook for college even, and there'll be a mention of 4 or 5 scientists and 1 or 2 things that they did, and that's about it. And certainly no real explanation of the work they went through to try and make their accomplishments. So this is my little teeny tiny attempt to correct that. Now, in the history of science, we usually start with the ancient Greeks and their attempts to explain things. And everybody, of course, is familiar with this, the 4 Greek elements: earth, water, air, and fire. And it seems pretty weird to us now, but actually that kept the alchemists busy for almost 2 millennia, until finally in about the middle of the 1500s, we finally started getting serious and less magical thinking about how the world works. Although there is one point about this that's kind of interesting. If you think of Earth as representing the solid state of matter, water, liquid, air, gas, and fire energy, you can see that maybe the Greeks were kind of pointing in the right direction. And also the Greeks were not completely monolithic. There were other theories as well. One of them was based on kind of a more mathematical approach instead of a physical approach. The idea was that if you had an extremely sharp knife and you took an apple and you cut it in half, and then you took one of those pieces and cut that in half and keep cutting it in half and in half and in half, that it wouldn't take very many cuts of the knife to come down to an incredibly small particle of apple. And they felt that there couldn't possibly be an infinite regress of that, so that there must be some point where you just couldn't cut anymore. There must be some particle that was indivisible. And so they called that particle the Greek word for indivisible, which was atom. And that's where the word atom comes from. So another interesting thing is that the Greeks knew about many different kinds of solids, the earth element. They knew about different kinds of rocks, different kinds of metals, wood. And they knew several kinds of liquids. They knew water, they knew alcohol, they knew various kinds of oils. But they only knew one kind of air. Nobody could conceive of any other kind of air, and apparently nobody ever even questioned that. Until about the middle of the 1500s, when some people started doing things like pouring acid on limestone or burning charcoal inside of sealed containers, and they found they had a kind of air that didn't behave like ordinary air. For one thing, it was much heavier than regular air. You could actually pour it into an open-top container like a pitcher, and then you could pour it out on, say, on top of a candle, and the candle would extinguish. And that was another thing about it that was different from regular air. It wouldn't support fire, and it wouldn't support the breathing of animals. So this fellow named Joseph Black decided to call this stuff fixed air. He had an idea that something about it was binding the air up and preventing it from becoming available for burning of fire or for an animal to breathe in. And now I want to have a little pause to talk about rich white guys. Unfortunately, all of the guys that I'm going to be talking about tonight were rich white guys. The fact of the matter is, at this time, chemistry was a hobby, and a very expensive hobby. So, well, I would love to say that there was some black woman in Port-au-Prince who did some fantastic chemistry discovery. Unfortunately, that's not true. So we just have to live with it, with the history that we have. So now on to the next picture. Whoops. This gentleman, Antoine Lavoisier. He's often called the father of modern chemistry. He did a lot of amazing work, and his job was collecting taxes for the French government, which got him a lot of money, and he had enough free time that he could build what was probably the greatest chemistry laboratory in the whole world at the time. Next to him, because he was a tax collector, he had a bookkeeper's kind of mind. He was very well attuned to the idea of balancing the books. And he brought that same idea to his chemistry experiments. He reasoned that if you had exactly 10 ounces of chemicals starting a reaction, after the reaction occurred, you should have exactly 10 ounces of products. And he was very careful about doing that. Was in fact one of the very first scientists to be so precise, and he helped kind of set the people that followed him on a path of precision that greatly helped the science. And this lady with him is his wife, Marie Anne. She was an amazing person, and in fact, in a less patriarchal society, she probably could have been a great chemist herself. She helped him quite a bit in his laboratory. She was much better at languages than he was, and she usually translated anytime he had a discussion with a scientist who didn't speak French. And the other thing that she did, which was very valuable to us even today, is that she made very careful drawings of all of his equipment, which is a big help when you're reading his descriptions of the experiments that he did. To actually see what the equipment looked like makes it much easier to understand what's going on. Okay, so now we're going to talk about the actual process of how they started to figure out what water was made of. Now, in those days, in order to discover what a substance was made of, they usually had two techniques. Either they'd pour strong acid on it to break it down, or they'd heat it very hot in a hot fire. Of course, with water, that's a problem, because if you pour acid into water, all you get is dilute acid. If you put water on a fire, it all boils away and you have nothing left to study. So he needed a technique to deal with that, and that's this. Now, this is one of Marie Anne's drawings here, and this is a flask full of water here on top of a regular ordinary fire. You can think of this as basically a tea kettle on a stove. Then it's connected to this pipe that sits in this very, very hot fire right here. Then the pipe comes out, it goes through this cooling coil right here, and then down into this glass jar. The cooling coil is so that any water vapor gets turned back into water and lands in the jar and gets separated from any gases that come out and go out this hose here. That hose would then connect to what he called a receiver. A receiver generally was a large glass jar filled with water, turned upside down and standing in a tray of water, with a hose feeding into the bottom of the mouth of it. This way, any vapors that came out would displace the water, and you could watch the vapors build up inside the receiver, and then take the receiver, keep it sealed with the water, and perform your experiments on it to determine what kind of vapors you had. And I've tried very hard to figure out if Lavoisier actually invented this setup or if he simply read about it. That was kind of his thing, is that because he had such a precise mind, he was always reading the papers of other scientists, and he often would read their descriptions of their experiments and would find things that he didn't like about it. They weren't carefully measuring the weights of the products, or they came to some conclusion that he thought was sloppy thinking. So what he would do is he would recreate the experiment, be as precise as possible, do it over and over again, make as many variations as he possibly could, and try to come up with more scientific explanations for what was being found. Now, the pipe here that goes through this hot fire, that was kind of a problem because they didn't have a lot of very heat-resistant materials in those days. So the first pipe was actually a long gun barrel. And whether Lavoisier did it himself or whether he read about it, anybody who performed this experiment with an iron gun barrel found that there was an amazing amount of rust inside the barrel in a very short amount of time. Now, to Lavoisier, this would be a total light bulb moment, because he had spent many years before this investigating why metals corrode. At the time, there was this idea that there was this rather magical substance called phlogiston that was somehow involved in it. Phlogiston was kind of interesting because it actually had a negative weight. The more phlogiston something had, the lighter it got for some strange reason. So Lavoisier looked at this and just tested the heck out of every possibility, and he came to the conclusion that it wasn't phlogiston, that in fact the metal was combining with oxygen, and that's what caused it to rust. So when he hears that there's a lot of rust inside this pipe, he immediately thinks, aha, oxygen is involved. So that's his first clue that oxygen might be part of water. Now, he eventually figured out a way to replace this iron pipe with a glass tube. He packed clay around it to make it so that it wouldn't melt basically in the fire. And with just the glass tube, he ran his experiment, ran the water through it, cooled it down, looked for vapor. He found he got a lot of water, did not get any other kinds of vapors out. So then what he did is he took his glass tube and he took thin sheets of iron, coiled them up, shoved them in the tube, ran the experiment again. He gets some water vapor, but he also gets a vapor that won't turn back into water. And so he starts investigating this, and he finds that um, as as everybody did in those days, he applied a flame to it. And the flame didn't get extinguished like it would with fixed air, and the flame didn't burn brighter like it would with oxygen. Instead, there was a small explosion, and he got this clear liquid. He looked at the liquid and studied it and realized it was water. So this new vapor, or what we now call a gas, he gave it the name hydrogen, which means water maker. And then he ran this experiment several times, did various tweaks to it, and eventually came to the conclusion that water was made out of hydrogen and oxygen and nothing else. So great, we got that, but now the question is, what's the formula? How much hydrogen, how much oxygen? Now, he knew that the weight ratios were such that if you took 1 gram of hydrogen, it needed 8 grams, almost exactly 8 grams of water, of oxygen to produce water. Now, you might be wondering, how did he weigh hydrogen since it's lighter than air? And the way he did that is he went to his metal workers and he asked them to make him an airtight can out of the thinnest possible sheet of copper that he possibly could. And they put a valve on it. And then what he did is he took this and he very carefully weighed it on a very precise set of scales with the normal air inside it. Then he took a pump and he pumped it full of as much hydrogen as he could possibly squeeze into there. If it was like, let's assume it was a 1 liter can, he might pump like 5 or even 10 liters of hydrogen into it. And then he would weigh it again, subtract out the difference, divide that by 5 or 10, and that's the weight of a liter of hydrogen. Did the same thing with oxygen, and that's how he discovered the 1:8 ratio. Now, this was kind of interesting. The fact that 8 is an integer says that, okay, maybe we're dealing with the number of atoms in a molecule of water, but how, we could assume that hydrogen and oxygen both weigh the same, in which case you get a formula of 1 H and 8 O's, but maybe oxygen weighs twice as much, and then it'd be 1 to 4, or maybe even it weighs 8 times as much, and it'd be 1 to 1. And he had no way of knowing. So we're kind of stuck at that situation. And then along comes the French Revolution, and poor old Lavoisier, because of his tax collecting activities, had an unfortunate encounter with the guillotine. However, about 2 months after he was beheaded, the French government sent a very nice letter to Madame Lavoisier and said they were terribly, terribly sorry about what they had done. So that made it all okay. Okay, so now we've moved on and we're into the 1800s. We're still in pretty much the same situation. There was one famous scientist called John Dalton. He decided that water must be simply 1 H and 1 O, but his only reason for deciding that was because that was the simplest formula it possibly could be, and he just felt that nature should be very simple. Other people had other ideas. It was all over the map, the people fighting all the time. And then along about 10, 15 years into this brouhaha, we get this gentleman. This is Amadeo Avogadro. And you can see why he spent a lot of time in the laboratory. But he was a very brilliant Italian scientist. And he looked at some rather interesting information that had been discovered. What had been going on is that ever since the fixed air discovery, there had been generally an accumulation of more and more gases being discovered. And of course, people wanted to know how those gases worked. And of course, they tested the flammability and all this other stuff, but they also would test things like they would have a cylinder with a movable piston in it, rather similar to the cylinder of a car. And they discovered that you could fill that cylinder full of any one of these gases, and you push up on the piston, squeeze the gas into a smaller volume, and the temperature went up. Or you could pull down on the piston, let it have a bigger volume, and the temperature went down. And this is very interesting. Every gas they tried did this. And what was really even more interesting is that every gas was virtually identical in this particular property. And this was crazy because we knew we had gases that put out flames, we had gases that made flames brighter, we had gases that would explode to flame, and they all seem to have different densities. And so why would they all have this one similarity? And old Amadeo here, along with a couple other scientists, around about 1820, said, well, we know that these particles must be very far apart from each other in relation to their size. Water, for example, when you go from a liquid to a vapor, expands more than 1,000-fold. So even if the individual atoms might be bigger or smaller in relation to each other, or heavier or lighter, when they're so far apart from each other, it's kind of like the stars. We know that there are some stars that are so large that not only could they dwarf our sun, but some of them could actually engulf the entire orbit of the Earth. And yet when you look at them in the sky, they all seem to be about the same size because they're so far away from each other and so far away from us. And he got to thinking, well, maybe this pressure, volume, temperature thing isn't really due to the properties of the individual particles. Maybe it's due to the number of particles in a given volume of space. And if that's the case, then suddenly we've got something we can do to have an apples-to-apples comparison of chemicals. Because if 1 liter of hydrogen has the same number of particles as 1 liter of oxygen or 1 liter of carbon dioxide, then we can do comparisons. When we do a reaction, we don't worry about the weights anymore, we worry about the volumes. And unfortunately, almost everybody ignored this because A, it seemed weird, and B, it caused a problem. So here's the situation. We've got 2 liters of hydrogen. We combine it with 1 liter of oxygen, and we get 2 liters of water vapor. So let's just forget about the hydrogen for the time being. Just consider the oxygen to the water. We don't know, or he couldn't know, how many particles there actually were in a liter, but let's just pick a number. Let's say that there were 1 million particles of hydrogen, of oxygen in a liter. So you got 1 million particles here, somehow producing 2 million particles here. So that doesn't make any sense, and he must be wrong. So let's ignore him. Approximately 50 years goes by, and it's still a big mess. Nobody can agree on the formulas. Everybody's yelling at each other. Finally, about 1860, a bunch of leading chemists wrote letters to each other and said, this has got to stop. Let's all get together at this town called Karlsruhe in Germany, and we'll just have a big old honking conference, and whoever's still breathing at the end of the day, their idea wins. So they did that. They would go there, and they had this big conference. And when they were there, they met this fellow. This is Stanislao Cannizzaro, another Italian. And he wrote a little pamphlet and passed it out to everybody, and he said, this is the solution to the problem. He said, the problem is Avogadro was right, and the reason you don't think he was right is because you guys don't know the difference between atoms and molecules. And in fact, that's true. The word molecule had actually been invented at around the turn of the 1900s, precisely because they started realizing that water, for example, you couldn't really call it an atom because it had to have at least 2 atoms, one of hydrogen and one of oxygen. So you got to call this thing something other than an atom. And they invented the word molecule, but then nobody followed the rules. Some people would call what we call an atom, they'd call it a simple molecule, and then what we call molecules, they call a compound molecule. Other people do it the other way around. They had simple atoms for atoms and compound atoms for molecules. And anytime you tried to read 2 people's papers and compare them, there was apples and oranges because nobody was being consistent. And so he finally laid down the law, and he said, this is an atom, this is a molecule. Amadeo Avogadro was talking about molecules. And once you do that, then you start to realize that, there is a solution to this. You may have 1 million oxygen molecules, but they could produce 2 million water molecules if each molecule has at least 2 atoms in it. Suddenly, the whole thing fell into place. You could do water, two H's makes H2O. Another gas that they couldn't make sense of before was hydrogen chloride, which is the gas that forms hydrochloric acid. And it was formed by 1 liter of hydrogen with 1 liter of chlorine, producing 2 liters of hydrogen chloride. So once again, H2 plus Cl2 yields 2 HCl's. And they tested it over and over and over again, and he was right, or at least his theory held up. So, H2O, it's possible that maybe it's not really H2 and O2. Maybe it's H4 and O4. But if that were the case, out of the thousands and thousands of reactions involving gases that have been tested, at some point we would have had a case where 1 liter of oxygen produced 4 liters of some other gas. And that has never, ever been found. So, while this is not proof, this is certainly the preponderance of evidence that oxygen is O2, hydrogen is H2, water is H2O. In fact, it's more than a preponderance. There is no evidence to counteract that idea. And this is why my science teacher was about 110 years out of date. This is why I think we need to be more teaching the history of science better. And that's the end of my talk. Thank you very much. Any questions? Mark has-
Avogadro, of course, is most famous for his number. Could you get into a little bit more, if you know much, about how he came about finding that?
Well, actually, he never did. He actually died a few years before the Karlsruhe convention, so he never even got to have his theory recognized in his lifetime. And even at this time, nobody knew what the number was. In fact, it took some rather clever mathematics to figure out what the number was relating to the mean path, the average path that a molecule takes before it bounces into another molecule. James Clerk Maxwell was involved in that. There was a German guy whose name starts with an L who was involved in that. And it took a very long time and a lot of really complex mathematics to actually figure that one out. Anybody else?
Yeah. Any other questions?
No? Hi, Larry. Wait.
Hold on there.
Mike.
Okay. Where would one go to get more history of science? Because apparently you say, like, and it's true. I've never. Oh. Okay. No, that's too much. Where would one go to find the history of science? Because I've never heard any of this stuff before.
Right.
And I took general science in high school.
Right.
But nobody ever brought any of this stuff to
Yeah,
the fore.
precisely my point. There are some books out there. Unfortunately, they generally don't stay in print too long. And because of that, they often are very expensive to buy even as used books. One of the best things you could do is start with Wikipedia and follow the links. One of the things I did was I went and I looked up Antoine Lavoisier's heading, and at the bottom of the Wikipedia article was a link to a download of a couple of his books. So I was actually able to, for free, get some of his books and start going through his thought processes when he was doing that. But it's definitely not served up on a silver platter. You gotta have some interest in it, which is, I think it would be nice if the history of science was offered as an elective at some universities or something, so that people could get spoon-fed a little bit more of this.
Larry, I got a bunch of books of history of science on my bookshelf if you want to borrow them or something. Particularly one that I don't have, but I read once was a history of medicine, or a history of surgery, which was kind of fun because they talked about how the digestive system works. Was discovered by this doctor who did some experiments on a guy who was shot in the stomach, and so he said, "Hey, I can sew you up, but I'd like to do some experiments on you." so he would like he made this flap so he could close it, and then he would shove various types of food in the guy's stomach, and then time them every like half an hour. He'd pull it out and see what happened, and another half hour, and keep going. And he did this over a course of a year, and he found that, well, the acids. He took the acid out of his stomach, and he did it in a test tube because people thought it was a bile or something magical about your body, and he realized it works just the same in his glass jug as it did in his stomach. So things like that. That's pretty interesting stuff.
Yeah. Great.
Since we're not heavily oversubscribed, I don't have a question, but a note on Avogadro's number. We actually still don't know the exact value of Avogadro's number, and we're still doing experiments to try to get it more and more accurate. And in fact, that is the limiting factor on trying to define the international standard of the kilogram in terms of physical constants. Yeah. And it's only just in the last year or two that they've gotten close enough where they can seriously get away from the physical prototype that's in a lab in Paris, because that's the last international unit of measure that's still based on an artifact rather than a physical constant.
Right.
Maybe they did change it, but if they changed it, it was recent.
Yeah. Avogadro's number is a really huge number. It's, I believe, 6.22 times 10 to the 23rd. And they do know it to several decimal places, but yeah, when it's a number that big, you're never going to get exactly what the number is. But the science is always held up, though, that a liter of gas has the same number of particles as any other liter of gas at the same temperature and pressure. Anybody else? Okay. Thank you very much.
All right, everybody.